The temperatures we've been having lately make lighting the forge seem like a really good idea. So that's exactly what we're going to do today. This is a project I've been wanting to do for a while, and we're going to build a Sanmai billet from mild steel and 125 CR1. This steel has 1.25% carbon and about 0.5% chromium in it. My main interest in this steel is whether or not it can be effectively used as a substitute for Japanese style or Japanese bladesmithing steels. I'm not talking about the Tamahagane sword steel, but the slightly more modern Japanese bladesmithing steels that they create over there and have been in use for quite some time. The main characteristics of these Japanese bladesmithing steels is a very high carbon content and little to no alloy content. So 1.4% carbon is common, is standard for these steels, and little to no alloy components otherwise. There are some other Japanese bladesmithing steels that do have alloy components in them, but the more traditional ones typically do not. The type of steel is directly related to how it is worked, and these steels lend themselves to the traditional Japanese bladesmithing techniques. There's some things that intrigue me about the Japanese bladesmithing tradition. It seems to be more rooted in practicality in many ways. Maybe that's because it's still connected to the methods that they used hundreds, if not thousands of years ago, when the entire purpose of a blade was utility. It had to work well because that's what it was for. I think a lot of that has been preserved in the Japanese bladesmithing tradition, and you still see it today. One of the things you see with this tradition, as well as other older bladesmithing traditions, is the use of multiple kinds of steel within the same blade. So rather than trying to get one steel to both be hard and abrasion resistant and hold a good edge, as well as be tough, they chose to combine two different steels to satisfy multiple different characteristics within the same blade. I'm sandwiching the 125 CR1 between the mild steel. We've forge welded it together, and now we're going to start drawing it out to make some blades from. The mild steel is tough because it's softer, it won't harden, and that high carbon steel in the middle will provide the edge holding, abrasion resistance, and hardness that we need to make a good knife. Combining these two allow us to make a very serviceable, durable blade when properly used for its intended purpose. I have enough here to make two knives from, and that's another thing that you'll notice. The small amount of steel that I started with in the high carbon content, that steel was very small. If I had used it by itself, I could get one small knife from it, whereas in this case, combining the greater quantity of mild steel, I have enough for two blades. So this is another characteristic of Japanese bladesmithing tradition that is interesting. You conserve the high quality, important steel, if you will, and overall that could lead to a more economical build. But of course, back in the day when good steel was hard to come by, this had a very practical application. So we've combined toughness and hardness in the same blade and conserved our materials. So far that's a win on both counts as far as I'm concerned. Because this steel has very little alloy component to it, I can work it in a very similar manner to the Japanese bladesmithing tradition. There seems to be no extraneous or extra trappings to the methods that the traditional Japanese bladesmiths use, which is another thing that's intriguing to me. It's a very practical, efficient process, but it does require a huge attention to detail and a fair amount of skill on the part of the smith. This is just something I'm interested in practicing, but having studied it a little bit, it is apparent to me that attention to the temperature and time and things like this in the moment of building the blade are important. There are no backtracking and doing grain refinement cycles to fix an overheated blade. That's not part of this process. As I'm forging the blade, I'll forge it down pretty thin, but I'm paying attention to the temperature, and especially as I near the end of my forging process, I'm working on keeping the temperature lower and lower just by a little bit each time I pull it out of the forge. This is going to help refine the grain of the steel as I'm finishing the forging process. The next thing I'm going to do is heat it up evenly, and it looks hotter in the camera than it really is, but a nice even heat up to critical temperature, as some would call it, but not any hotter than necessary, and then into a bucket of vermiculite to anneal. Now again, I'm able to do this because unlike steels like 52-100 or any other low to medium alloy steel, the 125 CR1 will respond to this anneal. This is my sample piece, and you saw me forging it, and we'll anneal it along with the blades. So the refinement of the steel is already taking place during the forging process, per the traditional method here that I'm trying to emulate in this project. The next step is all about removing the forge scale. This is a pretty effective way to do it, and you'll notice how soft the blade is. Now, 2/3 of this is mild steel, but if the high carbon steel in the middle of this blade was hard at all, it would not bend like this, at least not nearly as easily. You can see the forge scale collecting in the depression of the wood block there. And once I've bent it both ways, I can straighten it out. And that took care of almost all of the forge scale. The next step is cold forging, which I'll talk more about in a minute. This is the first blade, and I didn't get all of it on camera, but I did on the next one, and I sped it up just so you guys could see how much cold forging I'm actually doing on the blade. The idea here is to strike each spot at least once, flip it over, or repeat the process so everything is forged twice. These combination dies are not ideal for this, but I was able to make it work. This is something I was really interested in checking out, and that is drilling holes in the tang for the handle bolts. It went very well, and the steel was quite soft, and the drill bit didn't even squeak. It would not happen with steel like 52-100. That wouldn't work. My sample piece did get a crack from cold forging, but again, it is not cushioned by the mild steel cladding, and so the process is not exactly the same as with the actual blades. I'm hoping it's close enough, though, to give us a good idea of what the heat treat comes out as. This is the second blade. So I want to talk about cold forging for a minute. It's often confused with work hardening. That is not what we're doing here. Yes, there's going to be some work hardening that happens in the process, but what we're doing is mechanically creating dislocations in the steel. Dislocations are not a defect, they're a naturally occurring component of the crystalline structure of the steel. This is a documented metallurgical fact. Now, this doesn't actually help us until we heat it back up to critical temperature during austenitizing. Those dislocations provide renucleation sites for the new grains that form as the steel changes phases. And that is how cold forging helps refine the grain structure of the steel. Straighten the blade a little bit, heat it back up to an even critical temperature. Again, it looks hotter in the camera than it actually is. And I'm quenching in water. Now, traditionally, you would have a light clay coating on the blade to help even the effect of the quench in the water, which is important because water is not a very even quenchant. But I don't have that, so I'm doing a quick quench in water and then transferring to oil to make sure there's not residual heat that over-tempers the blade. The reason I'm using a water quench is because this steel, as with traditional Japanese bladesmithing steels, requires an extremely fast quench in order to harden to its full ability. Even a fast oil like Parks 50 would not be adequate to harden this steel. Some straightening, and this is another benefit of the mild steel cladding, is that you can work with the blade a lot more than you could otherwise. This is our test piece, which I ran through the same heat treat processes as the blades. I tested the hardness out of the quench, and strangely, it actually tested 2 points higher after I tempered it for about 10 minutes at 350. I'm not sure why. It might be because it hadn't fully transformed down to martensite, but I need to point out that my Rockwell tester is reading about 1.5 points lower than the actual hardness. Now, I ran my test block several times before testing my steel and after, and it reads consistently. And so rather than get up in the top and mess with the fiddly screws to adjust the calibration, I simply compensate on paper the 1.5 points. All that to say, we ended up with a Rockwell hardness of 63.5 to 64 on the finished steel. Hair popping sharp is when you can touch the edge to a hair on your hand or arm or whatever. With some gentle pressure, it'll just pop off. I don't know if I can get this on the GoPro here. Kind of push that one a little bit. So hopefully you can see that. I was able to get a very keen edge on this. The hardness is good. I'm going to put a handle on this and use it, but just a non-advisable edge retention test here. We can cut brass with it. Got a very thin edge on this, so it is rolling it a little bit. Which would happen with any steel. I ground this down to about 5/1000, 3/1000, somewhere in that neighborhood before I put an edge on it. So it's gonna show up on there. If I had the right edge geometry on there, we could whittle brass all day long and not see anything on here. But you probably can't even see what it did do on the camera. Overall, I would call this project a success. Am I going to switch out my typical 52-100 for this steel? No, I still think 52-100 is the best overall steel for most of the knives that I make. But I can see 125 CR1 as being a part of some kitchen knives and things like that in the future. As always, thanks for watching, and we'll see you on the next video.